Hi and welcome to the lesson about Introduction to Boolean Algebra. This is the first lesson in the bitwise operations series. Objectives of the lesson. We will use bits to represent the truthfulness of statements. We will learn about truthfulness of basic and complicated statements. We will study the representation of complicated statements using operators like not, and, or, and XOR. We will learn how to calculate the truthfulness of statements in a mechanical way. A bit more about the reason for doing this lesson. This lesson is a bit theoretic compared to the other lessons in this course, and I decided to do this lecture because I think it is a very important foundation for understanding the bitwise operations and the bitwise instructions. I could just teach you the bitwise instructions. There are actually instructions that do those operations, the not, and, or, and XOR operations. However, I think that some of you, those of you who don't have any theoretical foundation for those kind of operations, those kind of logical operations, those of you won't be able to understand the meaning of those operations. And because we are going to use these operations here and there in the rest of the course, I want to make sure that you are going to be able to understand the meaning of those operations. Actually, I believe that the meaning is a bit more important than the instructions themselves. If you can actually understand the meaning, whenever you get to another processor, you can very easily understand the instructions of the other processor, just because you can actually understand those kinds of operations, the not, and, or, and XOR. So let's begin. We begin with basic statements. We consider statements and their truthfulness. Those statements could be, for example, 3 is bigger than 2, or there is a triangle with 4 vertices. Those statements could be either true or false. So the content of the statement, at least at this point in this lecture, it doesn't really matter. The only thing that matters is that there are basic statements like those, like 3 bigger than 2, and there is a triangle with 4 vertices, and every such statement can have only one value, true or false. Either it is true or false. Intuitively, we can combine different statements into new statements. So let's begin with those two simple statements. 3 is bigger than 2, which is true, and there is a triangle with 4 vertices, which is false. Now we can combine those two into new statements, which are a bit more complicated. For example, this one. 3 is bigger than 2, or there is a triangle with 4 vertices. This is true. And why is that? Because the OR operator means that it would be enough that one of the statements, the first or the second, is true. And we know that this statement, 3 bigger than 2, is true. Thus, the whole statement is true. Let's look at another one. This time we use the AND operator. Here we have 3 bigger than 2, and there is a triangle with 4 vertices. The AND operator requires that both of the statements are true. But in this case, it doesn't happen, because this statement, there is a triangle with 4 vertices, is false. Therefore, the whole statement, all of this, is false. Another example. Here we can see the NOT operator. The NOT operator is just some kind of an inverse on the statement. It turns true statements into false statements and vice versa. So, because this statement, 3 bigger than 2, originally is a true statement, when we take the NOT of this statement, we get a new statement which is a bit more complicated, and its value is false. Maybe even just intuitively, it seems like every basic statement is either true or false. We can calculate the truthfulness of combined statements using the values of the basic statements. Simplified notation. So far maybe I can show you again in the previous slide, it was a bit cumbersome to write the whole statement every time. For example, this statement is really large, and as I mentioned before, we don't really care about the content of the statements. So maybe it would be a good idea, instead of writing the whole statement every time, we can just mark it with some English letter. And it would be a pretty nice shortcut. Some other shortcuts for representations. We were speaking about true and false. These are going to be represented by 1 and 0. And is going to be represented by this symbol. And or is going to be represented by this symbol, which looks like the letter V. Not is going to be represented by this symbol, which is some kind of a corner. If we have two statements A and B, we could represent, for example, A or B as A, this symbol, which is the OR symbol, B. And we could also represent A and B this way, A and B. We could represent not A as this expression, not A. As you can see, these kind of expressions are much shorter than the ones that we had in the previous slide. Some calculation rules. We take it a bit further, and now we are going to try to be a bit more formal, now that we have all the mathematical symbols. We begin with the NOT operator. It operates on exactly one bit. We also call this kind of operator unary operation. Unary means 1, as opposed to binary, which means 2. So NOT is an unary operator, as opposed to AND and OR, which are binary operators. The NOT operator flips the truthfulness of a statement, which means that the new statement is only true if the original statement is not true. Some very simple examples: not 0 is 1, and not 1 is 0. The AND operator. It operates on 2 bits, which turns it into a binary operator. What does it mean? It means that it takes 2 bits and it generates 1 bit. The AND operator results in true or 1 if the first argument is true and the second argument is true, which means that both of the arguments has to be true to get a true result. The OR operator. It operates on 2 bits, which is a binary operator, just like the AND operator. This operator, the OR operator, results in true only if the first argument is true or the second argument is true. So the marked words here, not, and or, are easy ways to remember the operation of not, and or operators.